Okay, up to this point, we've had derivatives with only one variable we've been looking at. That's not reality all the time. That's why we have a process called implicit differentiation. So we can have graphs of things that are more than just functions. Up to this point, we've just done functions with a single variable. Think about this for a second. What if I have a circle? Is that valid? Of course a circle is valid. What if I want to find the slope of a tangent line on a circle? Can we do that? We can after today. Remember, if I'm looking at a circle, the equation for a circle is a couple of them. If we're going to just look at the center radius form, that's y is equal to x minus h squared and the y minus k squared, right? And this is, no, why did I put that y there? See, I told you, you get in the mode sometimes. This should be r squared equals. That would have been a function. We're not talking about a function. We just said that. So if I'm looking at a circle, r squared is equal to x minus h squared plus y minus k squared. This is center radius form. This is just one example. I mean, there's lots of other things out there that doesn't have to be a function, right? If I have a center, that's what these values are, right? Is HK. That's the center of my circle, the center. If we have our radius, that is this R. Notice in my formula, R is squared. So to get my actual radius here of R, then we just take the square root of it. We're not trying to do this algebra. This is just algebra. This is just a side note of the center radius form. Man, I looked at that word circle, and it looks really rough, doesn't it? Let me try again. C-I-R-C-L-A. That's a little better. Okay, so here's where we're actually going to be using this. Scoot it up a little bit. Here is example 1A. So in example 1A, it says we are going to calculate dy dx for the unit circle. And then it's x squared plus y squared equals 1. Okay, so we're just finding dy dx in part A, and then part B is whenever we're going to find the slope of a specific point. Okay, I thought we were doing it all at once, but we're not. So here we are, the unit circle, just a normal unit circle, right? I know if I were to look at this x squared, x minus h, that's a 0 because there's nothing there. That's a 0. So for my center here, it's at 0, 0 with a radius of 1, unit circle. Okay. The other thing I want to point out, notice this notation. This means the derivative of y, and I'm going to put WRT, that's math term for with respect to. So derivative of y with respect to x. I'm pausing because how many variables do we have in this? We have an x and a y. But if I find the derivative of y with respect to x, now notice for implicit differentiation, you have to use this notation. There is no f, there is no function. I'm not talking about a function here. I don't have a y prime. I'm not getting y by itself. I am taking the derivative of y with respect to x. Okay, so x is the variable that I'm focusing on in terms of taking a derivative. Okay, so now I have x squared plus y squared equals 1. When you do implicit differentiation, the reason why notation is so incredibly important is because I'm going to take this derivative here of x squared. But because I'm taking the derivative with respect to x, we just straight up take that derivative. But what happens over here? My derivative is supposed to be with respect to x, but y is the variable. Okay, so this is kind of like a chain rule, is what's happening. So, well, it's not kind of like, it is a chain rule that's happening here. So I'm going to take the derivative of this y just like normal. So if I were to just take it, however, then I multiply by the derivative of the inside. And the derivative of the inside is always that y variable. So then I take it dy dx. So I am now taking the derivative of y with respect to x because y is that variable. Then over here it's a constant, and the constant, derivative of a constant is 0. So with implicit differentiation, here's the moral of the story. With implicit differentiation, you're going to take the derivative of x like normal with no big deal. With y, you take the derivative like you would, just take a normal derivative, and then you tack a dy dx. Pardon me, tack a dy dx on there. All right, now solve for dy dx. Isolate dy dx. So in order to do that, I'm going to subtract 2x from both sides. So I now have 2y dy dx is equal to a negative 2x. Divide both sides by a 2y. Now dy dx is equal to, and now those 2's cancel, right? A negative x over y. And that is my derivative. All right, so I divide by this 2y on both sides. I've subtracted that 2x, and then this is what I have left over. So when you have implicit differentiation, you're going to have two variables in your answer. Now, what is a derivative? What's another word for derivative? Slope of the tangent line, right? That's our Pavlovian response. So what if I want to find the slope of the unit circle at 1/2 square root of 3 over 2. Ah, so you're picking up on it. I love it. You guys are so good. I have both an x and a y. Normally, we just plug the x in because that's the only variable we have. But because I have both an x and a y, and the slope of the tangent line is the same thing as my derivative, right? We just talked about that. So I'm going to plug in both my x and my y coordinates. So here's the notation we're going to use. The derivative of y with respect to x, and I'm evaluating that at 1/2 square root of 3 over 2. So when you put a line next to it and then this value down in the bottom, that means that that's how I'm evaluating that. So I'm plugging that in. So a negative 1/2 over the square root of 3 over 2. Right? And when you have those same thing in that denominator, they just cancel. You don't have to rationalize this. Just leave it as negative 1 over the square root of 3. All right, do you see how this algebra played out? Negative 1/2 divided by the square root of 3 over 2, which is equivalent to negative 1/2 times 2 over the square root of 3, and those cancel. Okay, just making sure that our algebra is good, and then we're good to go there. It's not so bad, right? The moral of the story is you're going to take the derivative of y just like normal, but anytime you take the derivative of a y variable, you essentially chain it by tacking that dy dx on it, because the derivative of that y is dy dx. Okay, we're going to practice some more.